Um, certain certain forces uh, cause the energy of a system to be conserved, and when only those forces are acting, we can say that the energy of a system is conserved. I may or may not have mentioned briefly at the end of last class that if you add together the kinetic and potential energy of a system, that is equal to what's called mechanical energy. And if only forces that are related to potential energies act, which, as far as we know about, are gravity and spring force, then the mechanical energy of a system is conserved, meaning that the initial mechanical energy is equal to the final mechanical energy. If other forces act, the mechanical energy of the system probably isn't conserved. It could be if other forces act and they balance each other out. But if any contact forces do not in general conserve mechanical energy. If I push a block, then I'm adding mechanical energy to that system. Maybe I lift it up, and then I would, even if it doesn't gain kinetic energy, it would be gaining potential energy. Or if I push it, it might be getting faster, gaining kinetic energy. Friction and air resistance forces like that generally cause systems to lose mechanical energy. The energy is dissipated as heat, thermal energy, into the environment. Yeah, but if those forces aren't acting, if we just have gravity and spring, and then other forces we haven't really learned about, specifically electrical forces, magnetic forces, then the mechanical energy of the system is conserved. So if that is true, we can say that the initial mechanical energy is equal to the final mechanical energy, or to be more specific, we can say the initial kinetic energy plus the initial potential energy, which could be a combination of spring and gravitational potential energy, is then equal to the final kinetic energy plus spring potential energy plus gravitational potential energy. Depending on the situation, we may or may not use all of these terms. Obviously, if the initial velocity is 0, we get rid of this one. If there's no spring involved, we would get rid of both our spring potential energy terms. If we start and end at the same height, if we're on a flat surface, we can get rid of these because h naught and h final are the same thing, so they'll cancel out. So depending on the situation, we may or may not have all these. In fact, in most situations, we will not have all 6 of these terms. So you just have to figure out what's going on in the situation. If there's no spring, you ignore the spring potential terms. You can get rid of them. If there's no change in height, you can ignore the gravitational potential energy terms, and so forth. So in this case, energy is just transferred from kinetic to potential, or vice versa. There isn't any energy being added to or taken away from the system. Remember, the total energy of the universe is always conserved. So when I say the mechanical energy of a system is conserved, we're referring to an object, or maybe a collection of objects, so that in this particular area or within these particular objects, energy is conserved, or there's friction or something else acting, maybe not conserved. But total energy of the universe is always conserved. So we'll just work through a few examples of this. So let's say we have a child is at the top of a slide, and this is a frictionless slide. There are a lot of those around. So at the top of a frictionless slide, she slides 2.0 meters down the slide, which is angled at 45 degrees from the horizontal. She begins at rest. What is her final speed? Well, look at this. Okay, we've got our big conservation of mechanical energy equation, but what's actually relevant? Well, half mv naught squared, that's 0. She is not moving initially. There's no spring involved in the problem, so we can get rid of our two spring terms. We have some initial potential energy, we have some final velocity, and we may have some final height, but if we can set our 0 for potential energy to be where the child winds up, and then we can say our final gravitational potential energy is 0. So in that case, we then just have mgh naught equals 1/2 mv final squared, because all these other terms we can set to 0. And now you notice here, we've got a mass in both of these terms, so those go away, and then we can plug in numbers and calculate. So 9.8, h naught, again, we've got our slide, it's angled at 45 degrees above the horizontal, she slides 2 meters, the hypotenuse of that triangle is 2 meters, so this is our height, so that's going to be 2 times the sine of 45, and that's equal to 1/2 v final squared. And then we just do algebra, 9.8 times 2 sine 45, and then that's equal to 1/2 v final squared, so multiply by 2 to get the half to the other side, and then square root, and we find that she gains a final velocity of about final speed of about 5.3 meters per second. Okay, let's take another example. Let's say we have a mass of 58 grams, is on a horizontal frictionless surface. On a horizontal frictionless surface, it is pressed into a horizontal spring, compressing the spring. Whoa, I ran out of space there. Compressing the spring 3.5 centimeters. Spring has a spring constant of 71 newtons per meter. What is the speed of the mass when it reaches the equilibrium position of the spring? Okay, now we go. You can see there's no friction, nothing but spring force doing stuff, so we can say that the mechanical energy is conserved. And we look back at our big equation. Well, it's pressed into the spring and then released. So we've got some spring, mass is up against the spring, the equilibrium position is over here. Mass has been pushed in, and then it's going to be let go. So it's starting from rest. So V naught is 0. We do have an initial spring potential energy. Then we think, okay, well, we're on a flat surface, so we can say that's our zero for potential energy, so both of these terms we can then ignore. And then in the final scenario, we're back to the equilibrium position of the spring, so there is no spring potential energy, and we just have kinetic energy. 1/2 we can get rid of, and then we plug in numbers. So spring constant's 21. Remember, we need to convert everything to meters and kilograms. 3.5 centimeters. Spring's been compressed 0.035 meters. And our mass, 58 grams, is 0.058 kilograms. And then we can solve for the final. 71 times 0.035 squared. Divide out 0.058, and then take the square root to find that we had a velocity of about 1.2 meters per second.